Well, hi there, boys and girls. Figured we'd start off today's video with a little bit of flair and a little bit of excitement. So we've got a unicorn and a rainbow here, and I had to do this because like two of my favorite girls in the absolute world told me basically that I suck at my videos because they're not flashy enough or whatever, and blah blah blah. So anyway, here you go. It's some rainbows and a unicorn, and here we got some sparkle, and rockets, and yeah, okay. So there we go. Anyway, today we're going to do related rates, and related rates are a way of setting up problems where time is the independent variable. Gosh, listen to the pep in my voice. Woo. So what we're going to do is we're going to have a list of things that will help us set these up because they're not real easy. I'm going to do this every single time with these questions. Draw a picture in motion. I'll find an equation. I'm going to take the derivative with respect to time, which by the way, this means oh, look at that, it's purple. This means d dt, both sides. And I'll freeze a picture and solve. So let's just go get right after this. How fast is the area of a square increasing when the side is 3 meters in length and growing at a rate of 0.8 meters per minute? So we're going to draw a little picture in motion. I have a square where the area is increasing. So this is my picture in motion. Look at my square. It's getting bigger. He's growing up. It's a grown up square. Alright, so I draw my picture in motion, and then I'm going to find the equation that relates all my variables. And this is the hard part. What equation relates all of this stuff? Well, I've got an area and I've got a side length. So the equation that relates this is area equals one side squared. So I've done the first two parts. Let's look at those again. Draw a picture, find an equation. Now we're going to ddt both sides. And we're going to have to make heavy use of the chain rule here because these derivatives don't mac and cheese. They don't match. Area is a function of time and side length is a function of time. So when I take this derivative, the derivative of a is 1 because it's like a to the first, but then times a prime. So I'm going to call that dA dt. Now the derivative of s squared is 2s, but then times ds dt. That's the chain rule, again, because time is the independent variable and area and the side length are a function of time. So we want to know now how fast is the area of the square increasing. Well, dA dt is a derivative of area, and that tells you the rate of change. So we're going to freeze our picture, and we're going to label one side length as 3 meters. And we know that the side length is growing at a rate. That means derivative. That means that the ds dt, or the rate of change of the side length, is 0.8 meters per minute. So now we can just plug and chug. dA dt, which I'm going to call a prime because it's shorter to write and they mean the same thing, is equal to 2 times the side length is 3, times the rate of change of the side length, which is 0.8 meters per minute. Which by the way is 8 tenths. So I get 6 times 8 is 48 tenths, and the 3 had a units of meters, and I get meters squared per minute, and that works out to be 4.8. Let's do another one. A stone dropped in a still pond creates a circular ripple whose radius increases. Oh look, we're dropping this. You can imagine these concentric circles that you've probably done this before. It's actually very fun. The radius increases at a constant rate. That's a derivative. That means this number is a derivative, which is going to be dr dt, or r prime. That's what this is right here. At what rate is the area enclosed by the ripple increasing 10 seconds after the stone strikes the pond? So I've got a little circular ripple getting bigger. It's like a donut. Look, I have rainbows, unicorns, donuts. What else can you ask of your math teacher? Okay, so there's my picture in motion. Now, how is the area related to the radius in a circle? This is what you're going to have to come up all by yourself. The area is related to a circle by the formula pi r squared. Now that we have this, we ddt both sides. So I'm going to have a prime, that's the derivative of a, equals 2 pi r times r prime. You got to follow it up with the chain rule. Okay, now we have to have our picture here. We freeze our picture. This freezing the picture happens 10 seconds later. The radius has been increasing at 2 feet per second. That means our radius is 20 feet. Now what is r prime? Well, r prime is given to us is 2 feet per second. So A prime, which is what we're looking for, what is the rate of the area? How is that increasing? So A prime equals 2 times pi times r prime, which is going to give me an answer of 2 times 20 times 2, or 80 pi. Now let's take a look at these units. The r prime was in feet per second, and the 20 was in feet. So I'm going to have square feet per second, and that answer is E. Didn't mean to hit 3 there, but look, hey, look, there's a blue 3. Now, how exciting is that? Let's hit my select there. All right. All right, had to pause there real quick. Anyway, so tomorrow, this is just a basic setup. You're going to have different kinds of questions, but let's go back to our rules. And in class tomorrow, you have to pay attention to these and get done with as many of these as you can. But you're going to draw a picture in motion, find the equation. This is sort of the difficult part. Take the derivative with respect to time, freeze your picture, and solve. So I hope to see you guys tomorrow, and yay, calculus.